Hey guys, welcome to Unit 5.4 using the first derivative to test and determine local extrema. Let's start with a quick critical point review. So a critical point is when the derivative is 0 or when the derivative is undefined. So this is a graph of f of x. So the derivative will be 0 when it has a horizontal tangent line, and the derivative will be undefined when it has a cusp. It could have a vertical line, one of those. So right here, we can see it has a horizontal tangent line. So this derivative is going to be 0. So right here it also has a horizontal tangent line. So the slope right there is 0, which means the derivative here at this x value is going to be equal to 0. Right here it also has a horizontal tangent line, and it has one here as well. And right here the derivative is undefined because it's a cusp right there, or a corner. So the derivative will be undefined. So now you might be thinking, well, everywhere there's a critical point, we labeled all our critical points, we have a local extrema. Remember, a local extrema is a relative maximum, like this, at this point, or a relative minimum at this point. So, like, it could have areas around it that are higher, but relative, it's a maxima, or relative, it's a minimum. And we can see that's the case with all these here. I would say be careful about that, because with x cubed, let's find the critical points. We can just do it algebraically too. So we set the derivative of this equal to 0. So the derivative of x cubed is 3x squared. We set 3x squared equal to 0. And we get x equals 0. And we can see, yeah, at x equals 0, it has a horizontal tangent line. However, this point right here is not a local minima or a local maxima. So we're going to see a test on how we can test whether it is a local maxima or a local minima. But first, let's look at these two graphs. So x squared, 2x is the derivative of x squared. We can see that x squared will have a critical point when the derivative is equal to 0. So the derivative is equal to 0 right here. We can see on the derivative at x equals 0, it's going to be 0. So this is a critical point. X equals 0 is a critical point. So is this a local minima or maxima? Well, we can see from the graph it is a local minima. And we can see that we know it's a local minima because it's decreasing before and then it's increasing after. And on the derivative, when it's decreasing, the derivative will be negative. So it's negative before and positive after. So to check, to make sure that it's a local minima, in the derivative, f prime of x should be less than 0. Then it should become 0 at the extrema, or at the local minima. So it should equal 0, and then it should become positive, or go above 0. So that's how we know we have a local minima. And a local maxima is just the other way around. It'll go from positive to negative. So it'll go from positive to then being 0, and then it'll go to negative. So this is a local maxima, and this is a local minima, and then this is local minima, this is local maxima. Alright, so now let's go into a question. So this one says, assume f of x is continuous for all real numbers. The sign of its derivative is given by the table below for the domain of f. Identify all relative extrema and justify your answer. So we can see our critical points are going to be right here, right here, and right here. So our critical points are going to be at x equals negative 2, x equals 0, and x equals 3. So at x equals negative 2, let's just sketch this out. So negative 2 is right here. The derivative, this is the derivative, is going to go from positive to negative. At x equals 0, it's going to stay negative. And then x equals 3, 1, 2, 3, it's going to go from negative to positive. So an extrema will be when the derivative before the critical point is going to be one sign, and after the critical point it's going to be another sign. So as we can see, at x equals negative 2, before the critical point it's positive, and then after the critical point it's negative. So it's going to be going from increasing at that point to decreasing, and then that will be at negative 2. And then at 0, it's negative the whole way through, so it's going to be constantly decreasing at x equals 0. That is at 0, sorry. This is at 0. And then for x equals 3, it's going to go from decreasing to increasing, because the derivative goes from negative to positive. So from decreasing to increasing, and that will be 0.3. So as we can see from our little sketches, we have a minima at x equals negative 2, x equals negative 2, and we have a that's a maxima, and then we have a minima at x equals 3. So we have a minimum at x equals 3. And so how we just proved that? We knew it was -2 because we knew there was a max at -2 because it went from positive to negative. And we knew there was a min at x equals 3 because it went from negative to positive. So let's go to our justification statements for a minute. I don't think I have it on here. But to prove that something is a local maxima, we just have to say that f prime of x changes signs. Here, I'll just type it. To prove that something is a local maxima, as we can see, the sign changed from positive to negative, so we just say f prime of x changes signs from positive to negative. And then to prove that it's a local minima, we say that f prime of x changes signs from negative to positive. Alright, let's do some more practice, this time with a graph. So this is the graph of f prime of x. It's important to look at this first. It's the graph of f prime of x, and we need to find the local minima. So right here, at x equals -2, it goes from positive to negative, which means if we sketch out -2 on the original graph of f of x, it's going to go from increasing to decreasing, and that point will be -2. At 0, we can see is another critical point because the derivative equals 0. It goes from negative to negative, so it's going to go from decreasing to decreasing more. So that's 0. At 2 is another critical point because the derivative equals 0. It's going to go from negative to positive, so it's going to go from decreasing to increasing. So right here is going to be 2. So as we can see, that x equals -2 is a local minimum, so we can say min at x equals -2, and then for our justification, let me make that bigger, because f prime of x changes signs from positive, that's a maximum, I don't know why I wrote min, positive to negative. And then we can also see there's a minimum at x equals 2, because, so min at x equals 2, because f prime of x changes signs from negative to positive. So now that we've understood it with graphs, let's start going to functions. So now this one's already a little bit easier because it's given as our derivative, so we don't need to find the derivative. First, let's find our critical points. So we just set this equal to 0 because it can't be undefined. So x squared plus 5x plus 4 equals 0. We can go ahead and factor this into 4 and 1. So x plus 4, and then x plus 1. Alright. X plus 4 and x plus 1. So that means our critical points are going to be x equals -4 and -1. Alright, so now we have our critical points. Let's go ahead and make our little table. So at our critical points we have -4 and then we have -1. So we need to get a number that's less than -4. So now I'm going to show you two ways to do this. The first way is to just graph our derivative. So let's just graph it and then look at it, and then we can figure it out. So if we graph it, we have 1, 2, 3, 4, and then we have -1. These are our two x-intercepts. We know that this is a positive even function, so its end behavior is going to go from up to up. So we can start it up, and we're going to go down to -4, and then we're going to approach our second 0 at -1. And we can see that before, so from -infinity to -4, we know that our sign is positive at -4, obviously it's 0. From -4 to 1 to -1, we know that our sign is negative because it's under the x-axis. At -1 is 0, and then from -1 to infinity, our sign is going to be positive again. Now another way to do this is we can just find a number in this, so -5. This might be helpful to some people. We can find a number in this, so -5. We can find a number in here, so like 0. And we can find a number in here, so like, or not 0. We can find a number in here, so like -3. And we can find a number in here in this domain, so 0. And then we can just plug -5 into here, you'll get a positive number. Plug -3 into here, you'll get a negative number. And plug 0 into here, you'll get 4, which is a positive number. And that's how you can fill out the chart that way. Alright, now let's examine the chart. We're going from positive to our critical point to 0, to negative. So that means the original function is going to go from increasing to our critical point, which is 0, to decreasing. So this will be -4. So let's just sketch that out a bit. Alright, let's look at our next critical point, -1. It's going to go from negative, which means the original function is going to go decreasing, to -1, to increasing, which means this is going to be -1. So we have a max is going to be at x equals -4. And we're going to have a minimum at x equals -1. And there we go. Alright, let's move on. Now this function, we're not given our derivative, so we have to actually find the derivative. If you ever get lost or confused, the first step usually to all these questions is just find the derivative. So f prime of x, we're going to just use the power rule. We get 3x squared minus 12. And we need to set this equal to 0, but first I'm going to factor out a 3. So 3x squared minus 4 equals 0. So 3, and then we factor this, we get x plus 2, x minus 2. And then equals 0. So our x's are going to be -2 and +2. So these are going to be our critical points. So let's create our table. Alright. Our first point is going to be at x equals -2. And then our second point is going to be at x equals 2. Alright. So now that we got our table, obviously we can just graph our derivative. I like that method better than plugging in numbers, so I'm just going to go ahead and do that. So we have 3x squared. So 3x squared is a positive even function, so it's going to look the same. It's going to go from up to up. So we're going to start up. Our first x-intercept is at -2, so 1, 2 right there. And our second x-intercept is at +2, so 1, 2 right there. And it's going to end up. So it's going to approach our first x-intercept, cross the x-axis, approach our second, cross the x-axis again, and go to infinity. So before 2, it's going to be negative, or positive, then it's going to be 0. Then it's going to go under the x-axis, then it's going to be 0, and then it's going to go above the x-axis. So at -2, it goes from increasing to decreasing. So let's draw that out. Increasing to decreasing. This will be -2. And at 2, it's going to go from decreasing to increasing. So this will be 2. So we got a max. We have a max at x equals -2. And we have a min at x equals 2. Alright, let's move on. Alright, now I'm going to show you 2 ways of doing this. But the first way is going to be significantly easier, I think. But there's some problems. I don't know. The first way is going to be more straightforward. The second way is probably going to be easier for some people. But let's go ahead and solve this. Now, it's important to look. We're looking for the maximum value. So we're not looking for the x-coordinate of our maximum. We're looking for the y-coordinate of our maximum. So that's what it means when it says maximum value. Let's go ahead and first, the start of every problem, we just take the derivative. G prime of x equals 2 -2 sine x, because the derivative sine or cosine is sine x. Alright, so now we need to find our local extrema on this interval. So we need to find our critical points on this interval, so we can set -2 sine x equal to 0. So if we divide both sides by -2, we get sine x equals 0. Okay, sine x equals 0. At 0, it also equals 0 at pi. Pi is not on this interval, but 0 is. So we can say x equals 0 is the critical point. Alright, now let's test our x equals 0. So let's draw a little chart. So 0. And then we know at x equals 0, the derivative is going to be 0. But what's it going to be before 0? Well, let's plug in a number a little bit less than 0. Let's plug in -pi/2, because that is in our interval. So we plug -pi/2 into this our derivative. So we have -2 sine of pi over 2. Sine of pi over 2 is 1, so we have negative 2 times 1, which is negative 2. So our sign will be negative. Now let's plug in a number a little bit greater than 0, or like pi over 2. Sine of pi over 2 is 1, and so we have negative 2 sine, or sorry, this should be positive because this should be negative pi over 2. Sine of negative pi over 2 is negative 1. Negative 1 times negative 2 equals positive 2. And then negative 2 sine of pi over 2. Sine of pi over 2 is 1. 1 times negative 2 is negative 2. So this is going to be negative. So we go from increasing to decreasing. So this is x equals 0. So now we know that we have a local maximum at x equals 0. But before we can say this is our answer, we need to find our actual maximum value. So we need to plug in x equals 0 into our original function. So we have 2 cosine of 0. So cosine of 0 is 1. 2 times 1 is 2. So 2 is actually our answer to this question. Now if you're good with this, you can click off this video. I'm going to show you a bit of a trickier method that is actually easier on this, in this like sort of format. But let's just, so the first part is the same. We find our critical point x equals 0. But now we're going to take the second derivative. And I'll show you why in a second. But first, let's just take the second derivative. So we have the derivative of negative 2 sine x. The derivative of sine is just cosine, so we have negative 2 cosine x. Alright, so now let's remember what the second derivative means. If we plug in a value and the second derivative is negative, that means we have a function that's concave down. So if we have a negative, if we plug it into here and we get a negative number, that means the function is going to be concave down and look like that. If we get a positive number, that means the function is going to be concave up. So if we get a negative number, if we plug in our critical point and get a negative number, that is going to be a local maximum because it's going to be right here. If we can plug in our critical point and get a positive number, that is going to be a local minimum because our point is going to be right here. So let's go ahead and plug in 0 into our derivative. We get negative 2 cosine of 0. Cosine of 0 is, again, 1, so we get negative 2. So we got a negative number, which means it's going to be concave down, which means our point is going to be our local maximum. So now we know that 0 is the x value of a local maximum. We plug 0 back into our original function, and we get 2. Same way as before. Alright, that's it for this video. I hope if you have any questions, reach out to me, and I'll see you or my friend will see you in Unit 5.5.